The last presentation I did, I had to wear a mask and it was tough. We're going to be talking about oxygen to the bacteria. Well, I wanted to say oxygen to me. I couldn't breathe. So anyways, I was going to ask, how many deal with high-strength wastewater, commercial wastewater and so forth. But if you're all with local health departments or the state, I know the answer already. You deal with that on a daily basis. So what we're going to do is we're not going to get into any kind of a design aspects or anything like that, how to design a system and so forth, but just want to kind of highlight some of the variables that if we're getting into a design of a commercial site, especially with high-strength wastewater, what are those variables that we really need to pay attention to, because oftentimes we don't. So one of the first things that always comes to mind whenever somebody says wastewater is kind of hard to tell up in the slide is this picture right here of a septic tank with that scum layer popping up. Now, isn't that high strength? I mean, that's pretty strong wastewater to lift those 75-pound lids up. So, but that's not what we're talking about for high strength. So, but yeah, actually in that particular condition, kidding aside, is because we don't have any detention time, that is going to create high strength wastewater coming out of that system. So, uh-oh, wrong way. So right away when somebody thinks of high strength wastewater, they think of what? Restaurants. Because of what? Grease and oil. These pictures are, for instance, the one on your left there is actually a distribution box going out to drain fields. Obviously it's ponded because you can't see the outlet pipes and so forth. Grease and oil in there. So, but the common misconception is people think that, okay, if we have enough grease tankage and we capture that grease, then we can apply conventional sizing criteria on our system. So we're going to answer, can we or can't we? Skip to. So when we're sizing conventional type systems, it's pretty prescriptive, pretty easy to deal with. If we have a 3-bedroom home, 150 gallon a day design, for 450 gallons per day, say we have a loamy sand, half a gallon per square foot, so we're going to need a 900 square foot field and a 1250 to 1500 gallon tank depending on your sanitary code. So pretty easy to deal with. So now when we talk about commercial applications, oftentimes we still kind of apply that prescriptive mentality onto high strength situations. And for instance, with our regulations, if that flow is less than, that commercial flow is less than 1,000 gallons per day, you can apply your sanitary code. But that's, again, we're dealing with, your sanitary code's only addressing the flow volume, and we size everything by the hydraulics. And then we go into larger commercial flows, less than 10,000, then we're going to be applying the Michigan criteria information when we're designing that system. However, in commercial applications or Michigan criteria, we're still just dealing with the flow volume and we're sizing based on hydraulics. Now, Michigan criteria does recognize that there is something different about restaurant waste. So in one of the appendixes in the back, there's a section in there. Okay, if we're dealing with a restaurant now, you shall have more tankage. You're only limited to sand or loamy sand. Doesn't say why that we have to have this concern, other than we observe a higher failure rate on those situations. And it also indicates in there, well, you can have no more than 3 or 4 doses to that system a day. So if we have a large flow situation, we're sending a huge slug every dose out there, and so how does that affect our treatment? Doesn't address the situation that, say, we have a restaurant that in a 6-hour period discharges 1,000 gallons all at once. Well, conventional pumping systems or gravity is just going to go right out to the field. So it doesn't address how we handle those big peak flows either. So if you apply the new draft version of the criteria, that kind of hits more on where we should be when we're looking at commercial designs. And so what's the life expectancy of a residential system? Anybody?
Depends.
exactly. That's, I always like the fact that everybody, it's 25 years, 30 years. No, it depends. Depends on usage, depends on the maintenance and number of variables and so forth. So, but if we size everything properly, the homeowners are careful with their system, maintain it and so forth, we should get a very long life out of that system, right? 20, 30, 40 years. Now, in a commercial situation, what's that lifespan? Dave? Exactly, same answer. So it depends. However, it's much higher risk. And because there's a lot of variables that we often don't integrate into our design. And so back in my early days, when I first hired on, did a number of projects with fast food restaurant, McDonald's, and setting up some treatment systems and so forth, and talking to one of the corporate McDonald's project managers, he indicated that on average across the country, their restaurants see an average life of the drain field about 5 years. So, because of the number of the variables that we'll discuss here, oftentimes we can have a shortened life in that system. We're not going to have the life that we would expect out of a residential system. So, for example, we need to understand the practices within the particular facility. I was involved in an animal shelter. They're designed by square footage, number of bathrooms, and so forth. But in the design, they really need to pay attention to what is the operation inside that dwelling. In this particular case, they failed to recognize that there's 2 commercial washing machines going 12 hours a day. There's 5 dishwashers going 12 hours a day because all the animals get fresh. They get better treated than we do in the hotel here. You get fresh bedding every single day. Their bowls are washed multiple times a day, so high flow. So that system lasted 1 year because we didn't pay attention to what exactly is the operation that's going on in there. Restaurant, brewery situation, just understanding the fact that, as I mentioned in the beginning, that even if we remove that grease in a restaurant, we're still dealing with potentially high wastewater that we have to deal with. Another example might be is if we have an existing system, understanding the treatment performance in each one of those processes is important. So I was involved in one restaurant. They were having some issues. They were getting tired of pumping their grease tanks because it is very expensive. So they went online and bought an aerator and put an aerator in their grease tanks. So what do you think happened? Went belly up pretty quick. And we're going to be talking about grease and oil and why having an aerator in that grease tank in this particular example created problems. Some of our treatment systems that we design can inadvertently create high-strength wastewater. So for instance, we have a community on-site treatment system, and say we have grinder collection. Well, if we don't understand what happens with a grinder pump, it grinds everything into a slurry, puts a lot of those organics into solution, and it's very tough to get out. It's kind of like orange juice. You know, you can screen out the pulp, but you still have the orange. And so you got to rely on the bacteria to degrade that. And so for instance, a grinder collection, if we design a system based on a BOD of 150, and we're probably realistically have 300 going into that system, so it can create a problem. So the main point to go away from is, you know, in order to create a very sound design based on science, we need to think outside the box or think outside sometimes of our regulations and think of the variables that we need to consider, because the data that we really need is lacking out there in any kind of reference manuals. And so what we're going to be talking about, what we need to consider in the design is the source of the wastewater. How many sources? What are the characteristics of those sources coming from a facility? The fluctuations in the flow in that facility, high strength waste, oil and grease, chemicals in the wastewater, and have a thorough understanding of the operation within that facility, what's going on. And problem is, it takes a lot of effort to do that, to produce a good scientific design. And oftentimes what you find out there, designers, or what I find is oftentimes I'll get a call from a designer, hey, I need some help designing a particular advanced treatment system. Okay, well, we need to collect all this information. Well, I don't have money built into it. I have a contract with my owner. He goes, I don't have time. He goes, well, I can design it based on the criteria. Well, you can, but let's look at the effect that you may have to that system owner by doing that. So it takes a lot of effort, and it takes a lot of effort on behalf of regulators and so forth to ensure that those proper procedures are taking effect. So when we talk about the source of the wastewater, kind of understand that effluent quality depends on the influent characteristics, and the influent characteristics are influenced by the source of the wastewater coming into that system. So simply put, is every commercial site is totally different. And it doesn't matter if it's a McDonald's restaurant, every McDonald's restaurant is going to be different because of all the variables that we just mentioned, and that we'll discuss in a little bit more detail. So when we look at wastewater sources, residential, it's textbook. We have decades of research on that. We verify. It's pretty dilute wastewater. We have a lot of gray water mixing in with our black water. Now what we have to be concerned with is commercial gray water versus residential gray water. Residential is actually pretty dilute, and we can dilute down that black water and have a relatively weak waste strength, or what we use as a baseline waste strength. Once we get into some kind of a commercial application, well, we have a whole wide range. We can have 25 to 75% black water, or the same with gray water, or we can have 100% black water, for instance, on an office building. And all those are going to have different characteristics that can affect the design and the performance of that system. So once we get into commercial, typically, especially with kitchen waste, which should be considered the gray water, that's going to be very high in waste strength. And we'll talk about waste strength numbers, what those mean. So there is a difference between commercial and residential gray. So examples of commercial flow sources. So let's say we're designing a grocery store. We can't just think, okay, based on square footage at grocery store, we need whatever, 3,000 gallon a day design. We need to look at all the sources. So in a grocery store, there's multiple sources of input into that system, and each one of those inputs have different characteristics that can impact that system. So for instance, obviously you're going to have toilets in there, primarily for employees. Occasionally, probably some grocery store shoppers will use it, but we're going to have a meat department, and the rest of these are all gray water. So we have meat department that can have blood. It's going to have a lot of cleaning chemicals involved in that. Could have a fish department, same thing. We have cleaning chemicals. You have a lot of melting ice and so forth to deal with. Bakery is real harsh. You have a lot of sugars. You have dairy. You have flour and so forth. That really alters the pH. So we need to be concerned with that. A slop sink. Most grocery stores are big tile dwellings. Periodically they strip that floor wax and apply new wax. Well, that all goes down the drain. A lot of floor strippers have zinc in it, which is toxic to bacteria and so forth. And so we got to be aware of where that source is coming from and the impact. Now we get into convenience store. Oftentimes people, when they're getting into the design phase, well, it's kind of a rural store, so they're not, they have a bathroom. That's about it. Maybe they have some roller dogs, but that's all brought in, packaged food and so forth. So we have a tendency sometimes to kind of put our blinders on to the fact that C-stores are no longer C-stores. A lot of them are restaurants now. And so there's a lot of food prep, which can generate grease. Coffee bar, a lot of these places have contracts with their coffee suppliers that they have to refresh that coffee every hour, so a lot of that gets dumped down the drain. And we'll see what those inputs have, and obviously soda machines and so forth. So in a restaurant, those of you in the health department, probably a lot of you are generalists and work on restaurants, so there's various flow sources there. Need to be concerned with, for their dishwasher is a hot water dishwasher? Is it a cool water chemical dishwasher? It has a major impact on our performance of the system. Food prep, salad bar, generation of a lot of oil, fat, oil, and greases. That's why a lot of restaurants, not only to save costs, but to protect their system, serve you a little bit of dressing in their little cups, and I usually got asked for about 5 or 6 of those, but so there's all kinds of sources. Office building, oftentimes you kind of put our blinders on there. Well, they just have toilets. They don't have any kind of cafeteria or anything in there. Well, everything's low fixture now, waterless urinals and so forth, so we really concentrate that waste. And when we start talking about waste strength numbers, we'll see what those are. Now let's take a look at, consider the flow volume and the variations in those flows. Again, residential textbook, we have wealth of information to support what the industry knows on that. Pretty textbook as far as the variations in a flow, except probably for the past couple years with COVID, with everybody working at home. I'm sure this changed, but typically we see typical residents peak in the morning and peak in the evening. So when we're looking at the flow volumes and the flow fluctuations in the commercial, it's a little more challenging, and we really have to try, if we can, try to stay away from our reference manuals, because if you have 5 reference manuals, I guarantee you're going to have 5 different results. So which one do you use? So for a repair situation, try to get flow data from that particular facility. Obviously if they have an existing system, they have a failure, again, we want to mitigate any kind of health threat and so forth. And a lot of times we just automatically put them on pump and haul. Well, that can kind of skew our numbers when we're trying to design a replacement system. So food service, and again, when we're doing a repair, we want to capture those peak flows. We don't want to just pay attention to our average daily flow. We want to pay attention to peaks. Now, in a food service establishment, if you're evaluating that and it's during a non-peak, cash flow corresponds to wastewater flow. So you look at the number of meals during their peak. If during their peak periods they indicate we see a 25% increase in revenue, you can probably be pretty safe to assume we have a 25% increase in flow in those particular situations. For a new facility, we want to get true data from similar type facilities at similar locations. Again, as I mentioned, use McDonald's. Every McDonald's restaurant is different. Well, that is true. It depends on location, depends on the management within the building and so forth. So, and then of course we want to apply safety factors. So we need to go in there and try to establish flow on the existing system or something similar. So how do we do that? Well, there's a number of methods. We could have a water meter on a service line. If we have to, reference manuals, flow measurements from similar facilities. If we have a pumped dispersal system, we can look at the hour meters and counters on those pumps and get a very accurate flow recording. And if we have to, we can use pumper records, but we have to realize that somebody's on pump and haul, they're being ultra conservative on water because that's costing them big bucks to pump those tanks. So our hope is that there is a means of, and oftentimes for a lot of our rural facilities on a water well, there's no means of collecting that water. In my opinion, every water source, water well or municipal, should have a meter on there. So we don't get into a jam if we're doing a repair situation. It's like, oh, now we got to try to guess what the flows are. So when we're looking at flow characterization, what we really need to know is the average daily flow. Really need to pay attention to the peak flows and what the duration is and the frequency of those peak flows. And pay attention to special occasions. For instance, on a Mother's Day, it's the busiest day of the year in restaurants and so forth. Or December, when they're having all kinds of Christmas parties. Is that changing our values? So this is an example of an actual restaurant that I was involved in an evaluation. Measured flows, we were averaging about 1,200 gallons per day, or 8,700 gallons in a 7-day period. But we wanted to see what the peak flow was. So this is just a one-time measurement. But on a Friday, we measured 1,900 gallons. On Saturday, 2,600 gallons. So quite a bit more than if we were designed by this average daily flow. In fact, 52% of that flow in a week occurs in 48 hours for that dwelling or that restaurant. So, so if we miss that, we're going to have an impact on our performance of our system. So how do we combat flow fluctuations? We utilize flow equalization, which is nothing more than a properly sized tank, typically following our septic tank, grease tanks. And we're time dosing out to either another treatment component or out to our dispersal field. So what we have is we control the feeding of the bacteria out here, and we precisely program how often and what type of a dose volume we want to achieve, and we hold those big peak flows so they're not overwhelming our system. We can oftentimes design our drain field based on that equalized flow. It optimizes treatment, as I mentioned, because we're literally just spoon feeding the bacteria instead of giving it a huge slug of food and all of a sudden they just populate, and so we're kind of creating a little starvation effect and keep them hungry at all times. So secondly, it's very useful for monitoring any kind of flow changes. For instance, if they have a leaking toilet can put out an extra 1,000 to 2,000 gallons a day. Flow modulation or flow equalization can help track system potential issues of systems. So let's consider waste strength. Again, we use residential values as the baseline measurement. Anything above that, we would consider high strength waste. So here's a chart here. We're primarily going to be concerned with the biochemical oxygen demand when we're evaluating waste strength, and fat, oil, and greases, and suspended solids. So typical domestic residential system, you're going to have a range right here, 120 to 189, basically anything under 200. Typical, you're going to see about 120 to 140, somewhere in that range if everything's working properly. And one thing this chart doesn't have is fat, oil, and greases. Typically coming out of domestic septic tank, that is under 20. So kind of pay attention to those numbers because we'll use those as reference for the rest of the presentation. So treatment in soil, you have to understand that the wastewater coming in is actually food for the bacteria. So in the treatment by the soil bacteria depends on how much food's coming in and the amount of oxygen that's coming in. So oxygen is critical for any kind of treatment to occur in the field or in a treatment system. So if we have more organics that are being applied to that system than there is oxygen available to those bugs, we're going to start clogging soil pores. The bugs are really going to multiply real quick, start turning anaerobic, start producing slime protective layers, and then we get a potential of massive ponding to come into the surface, which would be regulatory definition of failure of that system. So fat, oil, and greases, once they get out there, if they short circuit that tank and they get out into that field, it's very difficult for the bacteria. It's a very stable organic compound, very difficult for the bacteria to degrade. It takes about 10 times more energy for those bacteria to degrade fat, oil, and greases than the typical organics that they're eating on. So because of the high oxygen demand for commercial wastewater, we may want to consider pressure distribution so we can spread that out and ensure we get good aeration through that soil. Usually the comeback on that is if a designer submits that to a local health department is, well, we have potential for fat, oil, and greases to get in that system. Those holes in the pressure distribution are going to clog up. And so my response back to that would be, if you have grease and oil and we're clogging up holes in the pressure distribution system, we've already clogged the pore spaces in our soil. It's too late anyways. And then also consider trench design versus a bed design to get better oxygen exchange. So again, the main thing is we want to make sure the pore spaces underneath our field are open so we get a lot of gas transmission, primarily the breathing byproducts of the bacteria, and oxygen transfer to occur. And in trenches, that has a shorter duration versus, say, this was a bed, this entire area is biomatted. We got to come a long ways for that oxygen to come through. So factors that influence the wastewater strength. I'm going to kind of click through these. I wasn't supposed to, there we go. So excess use. Again, if the system is receiving more wastewater than the system was originally designed for, that's obviously going to increase the waste flow. Low flow fixtures and so forth has a tendency to concentrate our constituents in that and can create high level wastewater. High organic loading, for instance, from a restaurant and so forth. Grease and oil, again, I've mentioned grease and oil will physically clog up the pore spaces and it creates a lot of food and massive bacteria growth. Again, remember that number of 20 coming out of residential. Once we start seeing numbers up around 25, 35, chances are we're starting to clog up those pore spaces and we're starting to jeopardize our system. pH. A lot of the chemicals that we're dealing with, grease and oils, and so forth, can alter our pH. The bugs like a pH between about 6.5 and about 7.5. Once it gets outside those ranges, those bacteria get real sluggish and they're just not doing their job that we need them to do. So we got to pay attention to pH and, and those flow sources, how can those impact our pH on our system? Temperature influences biology and the grease concentration. So the bugs thrive in a certain temperature. Grease and oil reacts, and we'll see in a little bit, reacts to temperature. And so we got to pay attention to that. Chemicals, pharmaceuticals, disinfections, obviously, impacts the biology, and also those same compounds will affect grease concentrations. Lack of detention time. That's pretty obvious. You have an undersized tank, and the flows are getting through, we're not going to get the degree of treatment that we need for our primary treatment. So we can consider separating that gray water from black water and deal with it that way. Get a little bit more detention time, for instance, for the grease tanks and so forth. So I already mentioned a collection system. We should be paying attention to various processes, make sure that they don't have a detrimental effect to our outcome going out to our system. So waste strength data lacks for commercial facilities. And if you were to look at it, we have a wide range. So it's not like a residential, we should be about 150. So those numbers are all over the board. And so we got to try to figure out what those are. Again, just like our flow, we want to try to collect from similar facilities. Pay attention to the management, the operation within that facility and so forth. Or if it's a new or an existing. And again, we want to try to get those samples during a peak period. If you were to sample a restaurant, for instance, the fat, oil, and greases on a Monday night when they really haven't seen any flow all day, you're going to get totally different results if you were to sample that on a Saturday night. So we need to try to sample. Then we want to collect a lot of samples. Composite sampling would be great on that, and that costs money though. So oftentimes we as an industry have a tendency, well, just kind of grab a sample at that restaurant. Okay, we got a sample, now we can design something. Well, you want to have multiple samples during multiple times of the day, to catch the variations that could occur during peaks and flow fluctuations and so forth. And then you want to make sure that whoever's collecting the samples, are they properly collecting the samples? I was reviewing some data the other day on a couple treatment systems out there, and the service provider, I know that they really don't collect samples on a routine basis. And I looked at their data, and the influence was way out of whack on 3 out of the 4. And so I need to go back and talk to them, how did you sample that? Because I've seen them sample before. I've seen them just use, pop bottles on a string and just kind of, get it in there and put it in the back of their truck. So I want to make sure that, what we're designing by are good, valid data points. So here's some of the concentrations that we're looking at. Again, office building, somebody, okay, that's an easy design. They just have toilets. Well, what we have to be concerned with, because of the low fixtures and lack of dilution, our BOD results, our waste strength can be elevated. Again, residential, what was that, 120 to 150? We can have flows or waste strengths up to 300 to 500. Rest areas, again, low flow, waterless urinals and so forth, can really have an impact on nutrients going in. We have extremely high nitrogen numbers, let alone the organics that we got to try to treat. So here's kind of an eye-opener. This is some data that was collected from University of Minnesota, a study they did on C-stores. The common thought is, well, it's a C-store, they got a bathroom, they got roller dogs, no biggie. But if you look at some of the other sources that are going in there, somebody goes and gets their big gulp, they realize, oh, well, I didn't want a Mountain Dew, I wanted a Coca-Cola, so whoosh, dump it in the tray, where's that go? Into the system. Well, what kind of impact does that have? Well, you look at Coke, has a BOD of 84,000 milligrams per liter. Again, residential is 150, so a little bit of difference. Really has a very low pH. They all have coffee bars, and they're always refreshing that coffee. We all like to have fresh coffee. And so BODs from a coffee is around 5,500. If you get into iced coffee, 168,000 milligrams per liter. And that's because of the sugars and the creams and so forth that we're putting in there, and low BOD. And of course, we're getting some dilution that's occurring. That's from the wastewater, the black water, and so forth. So typically, what you're going to see coming out of a C-store is a BOD that's going to range somewhere probably around 400 to 700 milligrams per liter. So if we just kind of assume that they have toilets and they have roller dogs, we can design it by hydraulics, we're gonna miss out on a proper design and potentially have problems with that system. So here's some more examples of some waste strength. This is some data that I had collected when I was working underneath Aquatest on some of their treatment systems they have. And so, here we go. So if we look at a fast food burger restaurant, those BOD ranges can really change. Multiple samples, we have ranges from 1,000 to almost 2,000. So that's where I'm kind of getting at. We have to get multiple sample points. We can't just sample one time and base our design on that. You look at the fat, oil, and greases, pretty high. What did I say? After about 25, 35 milligrams per liter, we really got to start watching it out. Something this high is really going to start clogging up our soil system. Fast food Mexican restaurant, BODs are relatively low on this particular restaurant, about 456. Oftentimes on some of the ethnic restaurants, you'll see very high, like Chinese restaurant, very high BOD numbers. Fat, oil, and grease is 70 coming out of this facility. Now, full service restaurant, we have a BOD of 900, so say 1,000. But look at the fat, oil, and grease is 235, and look at the pH, it's way down. So just kind of give you an example that, when we're comparing that to our baseline measurements, we can be way up there and really put us out of the ballpark in design. So fat, oil, and greases, again, very stable organic compound. It's very difficult for the bacteria to reduce that. The grease over time starts breaking down into fatty acids. And actually, if that tank's not pumped in a few months, you'll start seeing a big drop in the pH. It can go down to about 4. And in fact, some people are looking at, instead of, when do we pump that septic tank? Some people are evaluating, do we base it on pH versus sludge judging it and measuring the physical separation in there. So fat, oil, and grease concentrations vary greatly with the detention time, turbulence in that tank, so we have to make sure we have large enough tanks, and we have to watch how that input is coming into the tank to reduce turbulence. Chemicals, low temperature chemical dishwashers, they're going to discharge fat, oil, and greases. and temperature has a big input. So understanding fat oil and greases comes in multiple forms that we're dealing with in the on-site industry. This right here is, snapped this picture a couple weeks ago at a restaurant that I was eating at, and I know for over the years have replaced our field multiple times. So I looked in their pump chamber going out to the field, and look at all the piping, everything's just coated with grease. So no wonder they have multiple replacement systems. So fat oil and grease, most of the stuff that we're dealing is free oil. So we get, when it comes into that tank, very minute droplets that because they have less density than water, they're going to float up. Thus the reason why we have a grease tank and so forth to try to capture that free oil and let them congeal on the top. So, but we can agitate that waste stream and create mechanical emulsification. So kind of like taking Italian dressing, a bottle of that, and you just shake it up, and it all mixes up, and you let it set, and then you start seeing the separation occur. So same concept. So, so with detention time in a tank, the oil will separate and form free oil. If we don't have enough detention time, or we have excess agitation, excess flows, big peak flows coming in, or we're pumping into that tank and we're creating a lot of turbulence, we're going to start discharging oil through that system if we don't have enough tankage. So chemical emulsification, that produces very minute small droplets of waste or fat oil and grease. And it's very difficult for that to start separating. And oftentimes that'll get carried out through the tankage into the field. One of the main culprits of that is chemicals. Chemicals will do that, especially if we're using chemical low temperature dishwashers. That's going to have a tendency to produce that effect right there. So if they do have that, they want to make sure that they use detergents that enhance a rapid separation, meaning it's got a very weak emulsification. So there are detergents that they can apply that'll help minimize this potential. Dissolved oil, usually those are very harsh degreasers, chlorinated solvents and so forth. So, we definitely don't want that in our systems. So kind of hard to see in this picture, but well, grease and oil, the coalescing grease and oil is reduced. So we got to keep this in mind when we're designing this, is reduced by temperature, emulsifiers, and the lack of a quiescent environment or a nice, quiet zone for that separation to occur for that system. So this is some old slides that are out there from Bill Stuth that kind of looks at again, the sampling when you sample and also the temperature effects. So this one right here, you can't see that, but this is 75 degrees, this is 85 degrees. And you see 85 is starting to get a little bit milky, so we're starting to get a little bit of fat oil and greases exiting out of here. This right here, this was a system, say this was a sample collected on a Monday, and so temperature is pretty low, about 75 degrees. Say we went back out there and we sampled on a Saturday during the peak flow events in this restaurant. Temperature is 102. Like you see, it just carries out that fat oil and greases. Once we start letting it, as you can see in this example right here, once it starts cooling, it starts coalescing and separating and floating up. So again, when we sample can have a big impact in the size of our tank and the quiescent zone and so forth, has a major impact. And so grease tank sizing to save on time, I'm not going to get through all the calculations, but there's a number of references like the EPA design manual, uniform plumbing code. So there's a number of ways that a designer can calculate the volume of tank volume. And so are they all the same? No, it's like if you have, just like our references for waste strength and flow and so forth, you get 5 references, you're going to get 5 different numbers, so which one is right? So oftentimes what you find, a lot of these kind of produce a design of about a 1-day detention time. It's not enough. So whatever you calculate on there, a good kind of rule of thumb is double or triple it. Create some safety factor in that system. So Multiple tanks or multiple compartments. Some people think those are better, especially having a multiple compartment tank. But we got to be convinced. Well, first of all, let me back up. On our grease tanks, nothing more than a septic tank, except the baffles are elongated. So we have a temperature gradient in the tank, warmer water on top, so when the grease and water mixture comes in, the grease has a tendency to rise up and get captured. So, and then the same thing right here. So a higher grease concentration on top than we would have on the lower part. So that's why the baffles typically installed maybe 12 to 18 inches off the floor of the tank versus midpoint or 1/3 down like we would on a septic tank. But what we have to be concerned with is, say we get a lot of grease and oil right in here, and say our baffle wall just has a little 4-inch flow-through port like a standard septic tank. And so what happens to that, physics, you got a big volume right here, you got a little pass-through port, and then you open up again. What happens? We get an increase in velocity. So we can have a tendency to kind of pull things through that system. So maybe a double compartment tank may not be as beneficial as we think. So, but we have to consider that in design. So here's a example. This is a restaurant. They had 7,500 gallon a day design. It had failed. They had two 5,100 gallon grease tanks on here. Well, they went in and redesigned it, and now they have 30,000 gallons of grease tank on a restaurant. So sounds like a lot. So, but what's that? About 4 or 5 times the design flow. Another restaurant recently involved with 3,000 gallon a day design. Failed because of grease output into that system, part of it because of the management practices. But they went in, now we got 20,000 gallons of grease tankage. So far on both of these, seems like it's working. So it's a whole lot more grease tankage than what we would normally design for. So when we're designing for high strength wastewater, we need to convert the flow and the waste concentration into a mass. So what we need to do is calculate the pounds per day of organics that we're relying on that treatment system or disposal system to treat. So very simple calculation, gallons per day, concentration of our BOD or organics, and the conversion factor, and that produces pounds per day. Won't get into it to save time, but if we have multiple sources, for instance from that grocery store, we need to kind of commingle that milligrams per liter, so a very simple calculation to do that, and then we can produce a pounds per day that we need to treat. Now we have to beware, say you have a design of 1,800 gallons a day, you look at the reference manual and it states that waste stream should be 200 milligrams per liter. So we design that, plug it in a calculation, get 3 pounds of organics, so pretty easy to deal with. But beware that if we actually have 1,500 gallons coming into that 1,800 gallon design, we now have to deal with 22 pounds of organics that system has to rely on. So what's that going to happen or result in? It's going to result in a failure. So waste strength and flow volume characterization, just real quick here, is on a residential system, we know that if we're flowing at about 200 gallons a day, typical waste strength, we got about 0.23 pounds that system has to treat. And we know if it's properly designed, people taking care of it, we're going to get a long life out of that. So that comes out to 0.003 pounds per square foot. So we're taking those organics, just spreading it throughout our dispersal field. And so what if we apply that to a commercial application? So say we have a restaurant, 2,000 gallons a day, 1,000 milligrams per liter. That comes out to over 16 pounds of organics that we have to treat through that system. So if we design by hydraulics, medium sand, that's a 1/2 gallon per square foot, we need a field to be 4,000 square feet. If we design by what we know that we got a big safety factor in that residential organic loading, we spread that out, take a guess what kind of drain field we need. A little bigger than 4,000, right? So we need 55,000 square feet. So, you know, a little over an acre, quite a bit more than an acre. Or if we use the new draft criteria that gets us closer to that, So if we apply that to the new draft, basically we would need a field size of 28,000. So again, either way, significantly more than if we were just dealing with hydraulics. I'm going to skip through these because we only have a couple minutes here. So if we're applying this to the organic, if we don't have enough area in there, so what do? Well, we can design it by hydraulics like we do, but we really need to let that facility owner know they better start saving their pennies because they're not going to have a system that's going to last 20, 30, 40 years. Connect to a sewer, or we can add advanced treatment systems to it to handle that. So performance-based system, we really need to pay attention to all those variables that we just talked about. And really need to converse with that system owner on the cost. Because usually you get into pretreatment, very expensive. A little Chinese restaurant could be 150,000 or 150,000 system. Truck stop could be just under $1 million. So big financial impact that they have to consider. And if it's new construction, I've seen people decide we're not going to construct. We're going to go look for a sewer system somewhere. So we got to make sure that we have room on it when we're designing a system, that we have room in between all our components, because if they change something in their operation or a different type of facility moves in, new type of a restaurant, that's going to change our characteristics of our waste stream. We may have to add on to that, which is again, a tremendous amount of cost. So we can look at dilution. So for instance, RV dump station, campsites, a lot of campgrounds having problems. Everybody in the world went out and bought a RV unit. So they're all booked, and a lot of them are struggling now. So one thing we've got to realize, and I know Dave's going to touch on this tomorrow, is RV dump waste is extremely hot stuff. I mean, it's a toxic soup because they have all kinds of chemicals for odor control that are meant to suppress the bacteria that are producing the odor. So we can go on pump and haul, and this could apply to a slop sink on a grocery store too. So we can go into pump and haul. Nobody wants to do that, it's very expensive. Well, we got to use dilution. So sometimes, solution to pollution is dilution. If we have a main waste stream in there, we can time dose that high strength wastewater, whether a slop tank or RV dump station, into the main waste stream and dilute it down, so that no more than about 10 to 20% of this daily flow is comprised of this. So again, that flow equalization, hold it and slowly meter it out. So this is a typical process that you might have on a commercial system. Again, a lot of components involved. We're going to have grease tanks, we're going to have septic tanks, a flow equalization tank, we're going to, in this particular case, a couple different aeration units, a clarifier, and if we need to polish even more, we may have another secondary treatment system included on that system. So a little bit more complex, and we really need to get a good handle of our characteristics to produce that design. Here's a truck stop in southwest Michigan. Truck stop here, grease tank. We have a lot of grease tankage. We have flow equalization pumping up over here. We have the aeration units, the clarifier, and a very large drain field, low pressure distribution drain field that we're applying to. That's the tanks going in. So 3 10,000 gallon tanks and basically 12,000 gallons of flow equalization. Equalize out that flow. It's one of the aeration units going in. A lot of these bigger tanks, we have to go into either cast in place or panelized tanks. And here's a picture of the system. So any of those systems, we need to make sure they don't go in the ground unless we have some kind of monitoring program. Very high strength or very risky. If the system's not maintained, it will go belly up very quick. So in conclusion, we have to realize that every commercial site is unique in regard to wastewater characteristics, and we must intentionally design for that uniqueness. So for commercial facilities, design and construction must be made to address the flow, the waste stream, oil and grease, and chemicals going in that system. That's it. Lunchtime.